Chapter 20, Many Electron Atoms, Section 20.7, Microstates and Atomic Terms. Even a single carbon atom with the 1s2, 2s2, 2p2 electron configuration may have many energy levels. From the NIST website, we can see the first few energy levels are 0, 16, 43, 10,000, 21,000 wave numbers. Each wave number is 1 centimeter to the power of -1. So if you multiply this value by the Planck constant and the speed of light, you can get all those relative energies in Joule. But why so many energy levels? Well, this is just because a carbon atom has a partially filled 2p orbital. The 2p orbitals can accommodate up to 6 electrons. But over here we have only 2 electrons. When you put 2 electrons into the 3 2p orbitals, there are 15 ways of arrangements. They are called microstates. These 50 microstates may be grouped into 3 atomic terms. The lowest energy atomic term further splits into 3 energy levels, with 1 or 3 or 5 microstates. They correspond to the relative energy of 0, 16, and 43 wave numbers. And then there are 2 other atomic terms. They correspond to 10,000 wave numbers and 21,000 wave numbers. But now again, why 15 microstates? Well, let's imagine putting 1 electron into the 2p orbitals. Because there are 3 2p orbitals, and the electron can be alpha spin or beta spin. There are 6 ways of arrangements, also known as 6 microstates. The m sub L value, this is the z component of the angular momentum of the electron. It can be -1, 0, or 1. Because when you have p orbital, L is 1, the m sub L can be -1, 0, or 1. The ms value of the electron can be -half or +half. So we can take just any one of the 6 combinations. 3 options here, 2 options here, then in total we have 6 options for the first electron. Now after we put the first electron into the 3p orbitals, let's place a second electron in these 2p orbitals. Now there are only 5 options left, because no 2 electrons in the same atom may have the same set of quantum numbers. This is why the first electron has 6 options, but the second electron has only 5 options. So now we have 6 times 5, 30 possible arrangements. 6 for the first electron, 5 for the second electron. Only if the electrons are distinguishable. However, we know electrons are indistinguishable. So any permutation of the 2 electrons correspond to the same physical state. Therefore, there are only 30 over 2 factorial, which is 15 possible arrangements when we place 2 electrons in the 3 2p orbitals. What if we have 3 electrons in the 2p atomic orbitals? Well, the first electron has 6 options, the second electron 5 options, the third electron 4 options. So overall we have 6 times 5 times 4. But also we have 3 factorial different permutations. And then we need to use 6 times 5 times 4 divided by 3 factorial. We get a total of 20 microstates. When we have 4 electrons in the 2p orbitals, again we use the same formula, we get 15 microstates. 5 electrons, we get 6 microstates? Well, you might have noticed that if we have 2 electrons versus 4 electrons, in both cases we have 15 possible arrangements or 50 microstates. That's not a coincidence. It's just because over here when we have 2 electrons, we simply arrange the 2 electrons, in the 2p orbitals. Here, when we have 4 electrons, we imagine arranging 2 holes, the opposite of putting electrons, holes into the p orbitals. Alright, so whether you are arranging 2 electrons or 2 holes in the 2p orbitals, you get 15 possible arrangements. Now let's look at the 15 microstates of the subshell of the carbon atom. So we have M sub L to be -1, 0, or 1. And we have M sub S for the electrons that can be -½ or +½ So in the first row, we're looking at 2 electrons with the same value of M sub L. And one is alpha, the other is beta. In row 2, we put the 2 electrons into this column with M sub L equals 0. 1 alpha electron, 1 beta electron here. Same here, 1 alpha, 1 beta. But this is in the third column in which M sub L is +1. So these 3 rows correspond to a pair of electrons with the same value of M sub L. Now let's allow the 2 electrons to have different M sub L values. Then we can have the 2 electrons in this column, in the first and second column. So it can be alpha and alpha here, and also it can be alpha and beta here. And then alpha, 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 beta. Now we have beta, alpha, beta, beta. And then beta, alpha, beta, beta. And now over here again, we just list all possible arrangements. Alpha, 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 beta, beta, alpha, beta, beta. So no matter how you arrange these 2 electrons, you will end up with a total of 15 arrangements. That corresponds to the 50 microstates of the carbon atom or a silicon atom. If you are talking about silicon atom, well, it also has a partially filled p orbital. But for carbon, it's 2 p orbitals. For silicon, 3 p orbitals. Now we are looking at a group of electrons, not just 1 electron. We're looking at a group of electrons, a group of 2 electrons. So we will use this method to determine the atomic terms. We sum up the M sub S value, we sum up the M sub L value. So physically, we are looking at the Z components of the angular momentum and the Z components of the spin. And then we sum up the Z components. We just study the Z components for a group of electrons. Alright, let's sum it up. We have beta and alpha. So the sum is 0. Beta alpha, the sum is 0. Beta alpha, the sum is 0. Alpha alpha, the sum is 1. Alpha beta, the sum is 0. Now let's look at another example. This is beta beta. So the sum is -1. So we're going to sum up the M sub S. Over here we sum up M sub L. 2 electrons in the first column, so -1 -1 is -2. 2 electrons in the M sub L equals 0 column, so it's 0. 2 electrons in the +1 column, so it's going to be 2. Now over here, 2 electrons, one with -1, the other 0. The sum is -1. Same here, -1. Over here, you have -1 in the first column, +1 in the third column, so the sum is 0. So we just keep doing this. We get all those sums. Why do we do this? Because we now somehow will have information about the Z component of the angular momentum of a group of electrons. and the z component of the spin of a group electrons. When I say a group of electrons over here for carbon, it's just 2 electrons, but later you can see if we put 5 electrons in the d orbitals, and then that group of electrons, well, are equal to 5 electrons. So for a single electron in an atom, we know m sub l is from negative L to L, m sub s is from negative S to S. Alright, and because s, the lowercase s, can only be 1/2, so m sub s can only be negative 1/2 or positive 1/2. Now, when we look at atomic terms, for a group of electrons, we have the same rule, but different notation. For a group of electrons in an atom, we use uppercase m sub l. We use uppercase L. We use uppercase m sub s and uppercase s. Alright, so when L, the uppercase L, is 0, 1, 2, 3, 4, the corresponding symbols are uppercase S, P, D, F, G. The 5 rows highlighted in yellow correspond to the 1D term, with L equals 2, S equals 0. I'm going to get back to the previous page to show you the 5 rows, in which L is 2, S is 0. So 1, 2, 3, 4, 5. 5 rows. L is 2. So m sub L can be negative 2, negative 1, 0, 1, and 2. Alright? And also we have information about this. S, when S is 0, m sub S can only be 0. Alright? 0, 0, 0, 0, 0. Alright, again, we need to look at m sub S and m sub L at the same time. M sub S is just 0, 0, 0, 0, 0. Therefore, S is 0. M sub L is a series of numbers from negative 2, negative 1, 0 to 1 and 2. So we have a combination of S is 0, L is 2. S is 0, L is 2. And over here we write 1D. D is a symbol for L equals 2. That's the atomic term for the 5 rows highlighted in yellow. And now you may ask about this superscript. This superscript over here is equal to 2s plus 1. So 2 times 0 plus 1 over here, it's just 1. The atomic term is 1D, and we have 5 microstates. The number of microstates is the multiplicity or degeneracy regarding L, and the multiplicity or degeneracy regarding S. When L is 2, we have 5 different values for m sub L. When S is 0, we have only 1 possible value for m sub S. And now we have over here 5 options times 1 option. We have 5 microstates. Alright, again, this superscript 1 is 2s plus 1. It's the so-called spin multiplicity. Alright, this is the spin multiplicity, and then the symbol that corresponds to L equals 2. We have also 9 rows not highlighted in any color. They correspond to the 3p term. When you see this p, that means L equals 1. When you see this superscript 3, that means S equals 1. Alright, so you just look up the symbol here, SPDF, correspond to L equals 0, 1, 2, 3. When L is 1, it's P. When it's P, L is 1. Over here, 3 is 2s plus 1, so that means S equals 1. We have a spin multiplicity of 3, because when S is 1, m sub S can be negative 1, 0, or 1. Now let's look at the 9 rows not highlighted. Alright, so you have 1 here, 1 here, and 1 here. Alright, in this 3 rows, you have ms equals 1, 1, and 1. Now m sub L, negative 1, 0, and positive 1. Alright, m sub S can also be 0. So let's find 3 zeros. 0, 0, 0. M sub L again can be negative 1, it can be 0, and it can be positive 1. Now m sub s can be negative 1, negative 1, negative 1, negative 1. M sub L can be negative 1 here, so correspond to this, and 0 and positive 1. So why 9 rows? Okay, it's just because M sub S can be negative 1, 0, or 1. M sub L can be negative 1, 0, or 1. So we have 3 options for M sub S, 3 options for M sub L. In total, we have 3 times 3. That means 9 options. And those 9 options are 9 microstates. They correspond to the 3p term. The angular momentum multiplicity is 3. The spin multiplicity is 3. So 3 times 3, we get 9. Finally, there's one last row, because we have 15 microstates minus 5 minus 9. We have one last row highlighted in green. That corresponds to the 1s term. When you see S, that means L equals 0. When you see 1 here, S is 0. Unfortunately, we use the same English letter S for the symbol that corresponds to the angular momentum, and the same letter S for the spin quantum number. So that's a little confusing and very unfortunate, using the same letter for different meanings over here. But again, let's just look at the previous page. Let's look at this. 0 as 0. M sub S can only be 0. M sub L can only be 0. That means S is 0 from here, and L is 0 from here. So the idea is very simple. We're gonna just make some rectangles. The rows and columns are possible values of M sub S and M sub L. First, the yellow rows, they form a 1 by 5 rectangle. 1, that means M sub S can only be 0. 5, that means M sub L can be 5 different values. And then we can make a 3 by 3, well, you can say square, but also it's just a specific form of rectangle. Because M sub S can have 3 options from negative 1, 0 to 1, and then M sub L can be from negative 1, 0 to 1, so you have a second rectangle. The third rectangle is 1 by 1 rectangle. M sub S can only be 0, M sub L can only be 0. So really, you just try to group the 50 microstates into a number of rectangles. The rows and columns of the rectangles are the possible values of M sub S and M sub L. In this case, we can make 3 rectangles, therefore 3 atomic terms. And now we have the 3 atomic terms, and we can sum up the number of microstates: 5 for this 1D term, 9 for the 3p term, 1 for the 1s term. We sum it up, we get 50. Among the 3 atomic terms, 1D, 3p, and 1s, 3p has the lowest energy based on the following rules. There are 2 rules to determine which atomic term has the lowest energy. The lowest energy term has the greatest spin multiplicity, so you look for the largest 2s plus 1. Over here, this is 3, and then this is 1, this is 1. Obviously, 3p has the largest spin multiplicity, therefore the lowest energy. But if you have 2 or more terms with the same largest spin multiplicity, the one with the largest angular momentum quantum number L has the lowest energy. Alright, so sometimes you see 2 terms, both with the largest spin multiplicity, and then the second rule is gonna break the tie. You look for the largest L. Now, what is the physical meaning of the atomic terms? Well, an atomic term describes the angular momentum and electron spin of a group of electrons in the same atom. Remember, in general chemistry, we use the lowercase l and the lowercase s to describe the angular momentum and electron spin of a single electron. that's not interacting with any other electrons. But when you have a group of electrons, such as in carbon, you have 2 electrons in the 3 2p orbitals, there's some interaction. And we need to take care of the interaction. And this is why we need to look at the total angular momentum, total spin of the group of electrons. But why don't we look at this L vector and S vector directly? Why did we look at M sub S and M sub L? Well, it's hard to sum up factors. When you sum up factors, you need to consider its Z, X, and Y components. You need to sum up all those 3 components separately. But if you just look at the Z component of those factors, the Z component is just a scalar. So we can directly sum up the Z components as if they are just numbers. And therefore, we like to just sum up M sub L for a group of electrons. We sum up M sub S for a group of electrons. It's just easier that way. And then after we sum up this M sub L, we get the Z component of the group of electrons. Here we get the Z component of the spin for a group of electrons. And we do know this kind of rule. M sub L has to be between negative L and L. For a group of electrons, we have the same rule. This M sub L can be from negative L to L. And if this uppercase L is 1, M sub L can be negative 1, 0, or 1. When L is 2, M sub L can be from negative 2 to 2, with a degeneracy of 5. The lowercase m sub s can only be negative half or positive half. But when you have a group of electrons, and then you look at the Z component, well, the Z component can be from negative n over 2 to positive n over 2, where n is the number of electrons in that subshell. So sometimes s can be even 1, then m sub s can be negative 1, 0, or 1. So we did look at the carbon atom as example, and we saw this kind of case. Carbon has a 3p atomic term, and 3p, that means 2s plus 1 is 3, s is equal to 1. The Z component can be negative 1, 0, or 1, because we are looking at a group of 2 electrons. Also, s can be even more than 1. It can be 1.5. Then the Z component can be negative 1.5, negative 0.5, 0.5, or 1.5. It's called a spin quartet because we have 4 possible values for m sub s. Now let's look at the experimental data for carbon again. The first 5 energy levels of the carbon atom are 0, 1643, 10,000, 21,000 wave numbers. One wave number, well, you can just multiply this by h and c, the Planck constant, and speed of light to get joule. It's this much. It's about 2 times 10 to the power negative 23 joule, or 12 joule per mole, or 0.012 kilojoule per mole. So it gives you a kind of idea about how much those relative energy values are. You just multiply all those by 12 joule per mole, or 0.012 kilojoule per mole. Alright, we can assign those relative energy levels, the first 3 to 3p, and then 1d and 1s. You can see 1d and 1s have higher energy than 3p. 3p has the lowest energy among all, because 3p has the greatest spin multiplicity. Alright, and now, why does this 3p atomic term have 3 energy levels, 0, 16, and 43? Alright, very small energy spacing. You can see you need to multiply this 16 by this. It's roughly going to be 0.2 kilojoule per mole. 43 times this, it's only 0.5 kilojoule per mole. Really small energy spacing. Well, it's just because over here within this 3p atomic term, you have angular momentum, you have electron spin. Alright, angular momentum, that's the group of electrons rotating about the nucleus, right? And the spin, that's the rotation of the electrons about its own axis. So two different circular motions. And we learned that when we have a circular motion of a charged particle, such as an electron, we create a current loop, an electric current loop, and that creates a magnetic moment. All right, that creates a magnetic moment. And when you have angular momentum and spin, well, there are two different magnetic moments, and they can interact with each other. Okay, they can be aligned in parallel or anti-parallel, and they can be aligned in a way that they are perpendicular to each other. So between these two magnetic moments, there can be attraction, repulsion, or no interaction overall. So that's why this 3p atomic term splits into three energy levels. The lowest one, well, this is when the two magnetic moments attract each other. Over here, when there's no interaction, and over here, of course, when the two magnetic moments have repulsion between each other, then you have slightly higher energy. So now we have to create another quantum number J. J is from L minus S all the way to L plus S. So J is 0, 1, or 2 for the carbon 3p atomic term. Because when you see 3p, P means L is 1. When you see this 2s plus 1 is 3, S is 1. So when L is 1, S is 1, well, L minus S is 0, L plus S is 2. So we have three possible values for J. J can be 0 or 1 or 2. They correspond to this three different energy levels. Over here, J is just 0. Over here, J is 1. Over here, J is 2. Now, the coupling of the orbital motion and the spin motion of the electrons is denoted by the quantum number J. The orbital motion creates a magnetic moment. The spin motion also creates a magnetic moment, and these two magnetic moments may attract or repel each other, or there's no interaction. Three different options for the 3p atomic term of carbon. Now this J can be from the difference between L and S to the sum of L and S. For the 3p atomic term, J can be 0, 1, or 2. The energy levels now becomes this. L is the angular momentum. 2s plus 1 is the spin multiplicity. And J denotes the coupling between the orbital motion and the spin motion. And again, J has a range from the difference between L and S to the sum of L and S. When the subshell of interest is less than half filled, for example carbon, the energy level written this way, with a lower J value has lower energy. The level with a higher J value has a higher energy. So for carbon, it's less than half filled, so 3p sub 0 is the lowest energy level. And again, the relative energy levels of 3p0, 3p1, and 3p2 are 0, 16, and 43 wave numbers. Now let's look at oxygen. The atomic terms of the oxygen atom are the same as those of the carbon atom, because in the oxygen atom we have 4 electrons occupying the 3 2p orbitals, which is equivalent to having 2 holes or 2 vacancies occupying the 2p orbitals. And the arrangements of 2 holes correspond to the arrangements of 2 electrons. So for oxygen, we also have the 3 atomic terms. The lowest energy atomic term is 3p, followed by 1d and 1s. But there's a difference between the oxygen and carbon atoms. Well, for oxygen, the 3p2 has the lowest energy. For the carbon atom, 3p sub 0 has the lowest energy. Well, if the subshell of interest is more than half filled, then this energy level with a lower J has a higher energy. The level with a higher J has a lower energy. The main reason is when we are looking at the atomic terms of oxygen, we are looking at not the two electrons. We are arranging two holes or two vacancies in the 2p orbitals. So that's just the opposite to arranging two electrons in the 2p orbitals. So that's why regarding the J value for oxygen and for carbon, we have two different rules. When the subshell is less than half filled, then lower J value means lower energy. When the subshell is more than half filled, well, a lower J value means higher energy. So what if it's exactly half filled? When it's exactly half filled, well, you'll see the value of L is going to be 0. And when that's the case, when L is just 0, J can only be one value. J is equal to S, the spin quantum number. So in that case, we do not have to rank the energy levels with respect to J, because J can only adopt one value when the subshell is exactly half filled. So for example, if you have p orbitals, if it's exactly half filled, it's going to be m sub L will be minus 1, 0, and 1. So the sum is going to be just 0. Now let's look at the quantum number of the Z component of J. So what is J? J is the coupling of the orbit motion and the spin motion of a group of electrons. Now let's look at its Z component. Its Z component can be from negative J all the way to J. So also there's a multiplicity. The values of m sub J can be different. There are this many possible values, 2J plus 1 possible values, from negative J to positive J. When you place such an atom in an external magnetic field, each energy level with a J value will further split into 2J plus 1 microstates. So all those electrons will be kind of aligned in a way that interact with the external magnetic field. And this m sub J can be like from negative J to positive J. So all different kind of ways in alignment with the external magnetic field. So when m sub J is 0, that means, well, the Z component is just 0. There's no interaction with the external magnetic field. And then you can have minus J or plus J. So you can have like repulsion or attraction caused by the external magnetic field. So now in that case, with an external magnetic field, each energy level may split into 2J plus 1 microstates. For example, 3p0 split into just one state, 3p1 splits into 3 states, 3p2, this J is equal to 2, splits into 5 states in a magnetic field. In total, we have 1 plus 3 plus 5, that's 9 microstates, correspond to the 9 microstates in the 3p term. The number of states for an atomic term can be calculated in two different ways. One way is we sum up all those 2J plus 1. So J is 0, 1, and 2. So 2J plus 1 is 3, well, 1, 3, and 5. Sum it up, we get 9. Another way is to look at the value of L and S. We look at 3p. L is 1, S is 1. So basically you just do 3 times 3. It's also 9. Here's a example problem 20.7.1. Calculate the number of microstates included in the 4F term. In the 4F term, L is 3, S is 1.5. So L minus S is 1.5, L plus S is 4.5, so J value can be from 1.5 to 4.5. Here they are 1.5, 2.5, 3.5, 4.5. Now we're going to sum up the 2J plus 1. So 1.5 has a 2J plus 1 of 4, and this corresponds to 6, this corresponds to 8, and this corresponds to 10. So we can sum up the values of 2J plus 1, which is 4 plus 6 plus 8 plus 10, that's 28. Also, we can just look at the term symbol. 4, we plug in 4 here, that's the spin multiplicity. And F, that means L is equal to 3, 2L plus 1, that's 7, 7 times 4, we get 28. So using these two equations, we should get the same number. Now let's look at a table of the number of microstates and the atomic terms for various subshells with the lowest energy atomic term in bold font. So what if you have only one electron in the p orbital? Well, we have 6 options, right? So 6 microstates correspond to the 2p atomic term. Okay, when you see p, that means L is 1. When you see 2s plus 1 is 2, s is 1 half. Alright, s is 1 half, L is 1. The number of microstates is just 2 times 3, that's 6. P2, P4. Well, we have 2 examples, carbon and oxygen. 15 microstates. The 3 atomic terms are 1s, 1d, and 3p, with the lowest atomic term in the bold font. Now 3 electrons, 20 microstates. Well, it's just 6 times 5 times 4 divided by 3 factorial. We get 20. And we can group all these 20 microstates into 3 atomic terms. Over here, this one has the greatest spin multiplicity and therefore lowest energy. 4s has the lowest energy. And now let's count the number of microstates. Over here, the number of microstates is just 4. So 4 times 1 is just 4. Here it's 2 times 5, it's 10. 2 times 3, that's 6. 6 plus 10 plus 4, that's indeed 20. What if you have only one d electron, 10 options? It's 2d atomic term. The multiplicity for this d term is 5. The spin multiplicity is 2, so 2 times 5, that's 10. For d2, we have 45 microstates because the first electron, 10 options. The second electron, 9 options. 10 times 9, 90. 90 divided by 2 factorial, 45. Again, it's just because electrons are indistinguishable. When we have 2 electrons, we have 2 factorial different permutations. We need to divide that, so we get 45. And now we have we can group this 45 microstates into 5 atomic terms: 1s, 1d, 1g, 3p, 3f. So there are 2 rules to determine which term has the lowest energy. First, look for the largest spin multiplicity, so 3. We have a tie here, so how do we break the tie? Now look at the largest L. So for the F term, L is 3. For the P term, L is 1. I'm going to go with 3F, with the lowest energy atomic term. Alright, so if we have 3 or 4 or 5 d electrons, it gets just more complicated. It's doable, it's really tedious if we have 5 electrons occupying d orbitals. The number of microstates is 10 times 9 times 8 times 7 times 6 over 5 factorial. We have 252 microstates. And then we can make 8 atomic terms. Each atomic term corresponds to a rectangle with rows and columns that are the values of m sub s and m sub l. And among these 8 atomic terms, we can easily identify the lowest energy term, 6s, with the largest spin multiplicity.